A macroeconomic toolbox for descriptive analysis. Welcome to our 7th topic in this course, in which we explore some analytical tools for the analysis of the macroeconomy. Please read Chapter 7 in the textbook. In this topic, you will learn about exploratory data analysis, which are techniques to uncover patterns in economic growth and trends. I am fond of Wesley Mitchell's quote about the importance of careful measurement. Mitchell wrote that, "The quickest way to attain reliable results is to take great care in measuring the phenomena exhibited." Of course, great care does not mean the latest statistical method, or necessarily the most sophisticated method, but more often than not, some basic tool or growth rate to bring out the message in the economic data. You will learn 1. How to use descriptive statistics to analyze macroeconomic data trends, cycles, and volatility. 2. About annualizing growth rates. 3. About different growth rates and why some are more useful than others. 4. Simple ways that economists use to filter data. 5. The basics of seasonal adjustment of data. 6. Why volatility is important for economists and how it is measured. 7. Why understanding business cycles is important. And 8. Some useful economic websites for data. Note that although the textbook discussion is far more detailed, we will focus on the key tools and concepts that you should be aware of. Let's begin. The starting point is to ask, what is meant by exploratory data analysis? Our discussion of exploratory data analysis, or EDA, is really tied to a practical perspective that even John Maynard Keynes held. The term, exploratory data analysis, comes from the late mathematician and statistician John Tukey's 1977 book of the same name. Tukey said of his approach that it is, quote, about looking at data to see what it seems to say, using simple arithmetic and easy-to-draw pictures. Unquote. Tukey further observed that there is a considerable variety of simple techniques for looking at data effectively. In 1962, Tukey noted that it is far better to get an approximate answer using simple techniques to the right questions than an exact answer to the wrong questions using sophisticated methods. John Maynard Keynes concurred with that view, though he lived earlier than Tukey, when Keynes said, "It is better to be roughly right than precisely wrong." So our practical perspective is to try to tease out those economic stories from the economic data using simple techniques first. Why is exploratory data analysis, EDA, important in economics? EDA is primarily used to see what data can reveal before any formal modeling or hypothesis testing task, and provides a better understanding of dataset variables and the relationships between them. It can also help determine if the statistical techniques you are considering for deeper data analysis are appropriate. We have discussed several simple theories about economic relationships, such as the relationship between the unemployment rate and inflation, or profits in the business cycle, many of which could not have been hypothesized without exploring the data patterns and relationships. To be sure, there also are plenty of economic theories that have been crafted ahead of data availability to test the hypothesis. But even those theories need to be judged against economic data at some point to be validated. What are some of the basic exploratory data analysis techniques used in economics? Economists start data exploration by determining how the data should be looked at as levels, such as interest rates or the unemployment rate, as changes, such as with inventories, as growth rates, such as with employment, inflation, real GDP, as episode or event changes, such as from a cyclical peak to a cyclical trough, as period changes, such as decade growth rates, or based on some other meaningful measure of economic change or trend, such as expressed as a natural logarithm. Then EDA methods are applied. Since we have encountered the use of growth rates, how would you answer the question, what is a growth rate? A growth rate measures the percentage amount of change relative to a base period. Since it is often misused, the note on this slide highlights an important point about discussing growth rate changes. In discussing growth rates, the percentage sign is used to indicate the change from the base period. However, when discussing a change in growth rates, then the correct presentation is as a difference between growth rates, represented by percentage point differences, not a percentage difference. For example, if the inflation rate went from 8% to 3%, then that is a 5 percentage point difference, and not a 5% change. Please keep this in mind. What growth rate formulas are relevant to analyze economic activity? Although we discussed how the BEA computes real GDP annualized growth rates for quarterly data, there are numerous formulas that could be used to look at growth rates. For example, it is common to look at year-over-year growth rates of consumer prices. As a rule, the longer the span between the numerator and the denominator of the growth rate formula, the smoother it is. But the turning point will take longer to recognize or see in the data, since the math itself introduces a recognition lag. Another point is that standard growth rates can be approximated using natural logs. Economists sometimes use a natural log change in their presentations, which may look formidable, but may be nothing more than a growth rate. The table on this slide shows relationships between the standard growth rate and natural log formulas. This slide shows an example of turning points in growth rates for the CPI, as measured as a 6-month smoothed annualized rate, which business scholars Jeffrey Moore and Victor Zarnowitz advocated as a smoother, but more timely growth rate than the year-over-year formula. For example, the 2008 high and subsequent low in the 6-month growth rate of the CPI preceded the year-over-year growth rate. This is simply a function of the formula used. Similarly, we could see that the annualized month-over-month percentage change in the CPI had highs and lows prior to either the 6-month smoothed annual rate or year-over-year CPI growth rates. However, it also shows that the month-over-month pattern of growth rates is far more volatile than either of the other two formula calculations. This slide demonstrates the difference between the standard formula for the 6-month annualized rate for the CPI versus the natural log approximation of the same formula. For the most part, the two calculations are indistinguishable, with a slightly larger deviation in 2021 when inflation was very high. The final example is the calculation of an average annualized growth rate over multiple years. In this example, the annual CPI is shown between 2000 and 2023. Then the average annual growth rate over that span, which is a span of 23 years, is the final value in the span, divided by the initial value, then raised to the power of 1 divided by the span. This calculation is shown on the slide. Of course, this also will work for other frequency data. If you had quarterly data, the span would be 4 times the annual number of observations, and you would have the value 4 in the numerator of the power, instead of 1. The numerator value in the power ratio represents the frequency of the data. Why do economists use the natural log transformation? It is a practical reason that taking the natural log transformation of the data will create a more linear pattern. An example of this is shown on the slide. On the left-hand side is a plot of the original data, which is nonlinear. However, after the natural log transformation. Then the relationship is log linear, that is linear in log form. How should economic stability be measured? Stability is an economic goal. But the measurement of it is done as the absence of stability, based on statistical measures of dispersion of data. The most common measure is standard deviation. Note that the standard deviation is the square root of the variance, and economic studies have used that concept to assess whether economic growth and inflation have become tamer over time. Here's the formula for the standard deviation. For economic analysis, however, a slight variant on this formula is to look at a moving standard deviation over some span of time. An example of this is found in Chapter 15, which looks at the volatility in the economy over time. What is an economic time series? Of course, we discussed what time series data is at the beginning of this course, when we looked at graphing different types of data. So, how would you describe a time series? An economic time series is a sequence of time-ordered observations of an economic statistic. Thus, every observation is associated with a unique time period, and each period refers to an equal time unit. For example, months, quarters, or years. Observations are sequenced by the time unit. Okay. We discussed some basic tools to look at volatility, growth, and long-term trends in the economy. However, when we think about movement in economic activity in the short-term time series, it is due to various factors, which led Warren Persons to suggest a way of conceptualizing how to examine those factors. What is Persons' method of time series decomposition? In 1923, Harvard University professor Warren M. Persons suggested one of the earliest methods of analyzing a time series by segmenting it into 4 types of variation. 1. Seasonal variation, which is an inter-year recurrent pattern. 2. Trend variation, which is its long-term movement. 3. Cycle variation, which is a wave-like movement, generally not periodic, that is a wave of a constant duration. And 4. Irregular variation, which is the remainder that is characterized by irregular fluctuations. We will look at each of these variations. But remember that you have already encountered the idea of segmenting a time series for conceptual analysis when we discussed real potential GDP and the natural rate of unemployment, that statistically stripped out the business cycle influence of real GDP and the unemployment rate. In this case, however, it is more of a statistical segmentation than what was done for real potential GDP and the natural rate of unemployment. The Persons approach underlies how data is looked at today. Most data that we have looked at is expressed on a seasonally adjusted basis. Although methods to do that adjustment have changed over the years, the basic approach is logically consistent with the Persons approach. So, what is meant by seasonally adjusted data? A seasonally adjusted time series removes the seasonal component, that is, the inter-year recurrent patterns that may be triggered by national or religious holidays, school years, etc., leaving the trend, cycle, and irregular components intact. The slide shows retail sales data, both seasonally adjusted and not seasonally adjusted. The red line has the recurring inter-year pattern due to holiday shopping, in which retail sales spike in November and December. The seasonally adjusted measure statistically removes that recurring pattern. Let's consider the process to adjust a time series for its seasonal pattern. Obviously, the seasonal pattern adds volatility during the year, but a month-to-month or quarter-to-quarter pattern, in the underlying trend and cycle, is what really matters to economists for analysis. So, how do we adjust the data to remove that inter-year seasonal pattern? For this example, let's take total non-farm employment for the state of Arizona. These data are shown on this slide, arrayed by month, along with its annual average. Step 2. To derive a simple seasonal adjustment factor, is to divide each month of the year by its annual average. Months with values of that ratio over 1.00 are seasonally strong months, whereas months with values under 1.00 are seasonally weak. By doing this for each year, you can see the implicit seasonal pattern during the year. Step 3 is to take a snapshot of that seasonal pattern over some representative years and average them for each month. In this case, we took the observations from 2010 to 2020 and averaged the values for January through December. Then those monthly averages become simple or crude seasonal factors that could be used to adjust future months. Of course, this assumes that the seasonal pattern is stationary. That is, does not change from year to year. Next, divide the not seasonally adjusted, or raw, data by that derived seasonal factor, which will yield an estimate for the seasonally adjusted time series. This is shown in Step 4. The graphic on this slide shows both the raw data and the seasonally adjusted counterpart, using those crude seasonal factors. It is not perfect, as you see, but does eliminate most of the inter-year pattern. Finally, the BLS's seasonal adjustment of those employment data for Arizona is shown alongside those generated using our derived simple seasonal factors. Numerous other adjustments go into the X13 seasonal adjustment process that is used by government agencies, which produces a smoother pattern. However, the basic concept shown here is the fundamental that is used to search for those recurrent inter-year patterns and to adjust for them. What is a trend? A trend is defined in the dictionary as the general direction of movement over time. It is thought of as an evolving pattern that is slowly changing over a long-term horizon, or period. Note that economists use the word trend interchangeably with the word secular, or sometimes secular trend, which may be redundant. A secular pattern is one that persists over an extended period. How should economic trends be analyzed? There is no one answer to how an economic trend should be measured. Two common ways to measure a trend can be based on 1. Historic trends, that is, calculated over some historic period. Or 2. Prospective trends, that is, calculated based on a projected changing pattern. Finally, irregular variation in a time series is basically noise, and makes it difficult to interpret the message from the data. So, how do economists analyze very volatile or noisy time series? Very choppy data can be viewed using what is known as a filter. A filter is simply a transformation of the data, using some statistical method. One of the simplest data filters is a moving average of the original data series. The chart on this slide shows an example of using moving averages to smooth out the noise in a very volatile time series. Although the Pearson's method of segmentation allows us to statistically derive a component of a time series dubbed the cycle, business cycle analysts use a different technique to compare business cycle episodes. How do economists analyze a business cycle? Using a basic NBER method of recession recovery business cycle patterns analysis, data is organized into business cycle segments of common duration, before and after a turning point date, and then each business cycle segment's relative share of that segment's turning point value is calculated and compared. In essence, the episodes are arrayed, such as the example shown on the slide for the CPI. In that example, the past cycles 12 months before the turning point in the economy, and 18 months after a turning point, are arrayed and divided by each episode's average to normalize the comparisons. So, this showed that a year and a half after the trough in the business cycle in April 2020, the CPI accelerated, but the 1980, 1949, and 1975 inflation bouts were more rapid than experienced in 2020. Is the irregular component of a time series analyzed? Generally, not. Traditional NBER, or person's decomposition of a time series, will calculate that irregular component, which is simply the unexplained residual, after subtracting the discrete trend, cycle, and seasonal components from the original time series. It is not analyzed. What lessons have been learned and shared for applying measurement techniques? The key lesson is to use them, but be aware of their limitations. And remember the economic principle, known as Occam's razor, which has come to mean that given competing options, that is, theories or methods, the simplest method should be preferred. What are some key U.S. and international economic data sources for analysis? Take a moment to consider some of these websites for major economic data sources. Of course, some of the data from those sources are consolidated into other databases, such as FRED. Also, there is a consolidated summary set of data that is compiled in an online publication called Economic Indicators by the U.S. Council of Economic Advisors for the Joint Economic Committee of Congress. This publication could give you an overview of key economic data available, especially used by policymakers. Some sources of data are specific to the department, such as data from the Bureau of Transportation Statistics. Although we have discussed the Bureau of Labor Statistics, the federal government has 3 bureaus of statistics, found in the Departments of Labor, Transportation, and Justice. The Treasury Department is a key source of interest rate yield curves and federal finance data. Treasury also houses the Internal Revenue Service, which compiles the statistics on income data that provides insight into income distribution and tax burdens by taxpayers, both individuals and businesses. The Energy Department compiles a comprehensive data set on energy use, production, and distribution along with forecasts. Of course, we have discussed the CBO as the source of potential GDP data, but the CBO does detailed studies on all aspects of federal financing. For international perspectives, the United Nations compiles data in lots of different social, economic, and demographic areas. 2 other international organizations for data are the OECD and the IMF. Although not shown here, I might add the World Bank is yet another source of international financial data. There are useful consolidated databases that you can use for free. This last question is more to underscore that point. Are there free economic databases of statistics available for analysis? Hopefully, you have a resounding yes to that question, and have been using at least the FRED database for assignments. However, please keep in mind that these consolidated free databases will not include all of the data available from the organization websites that we just reviewed. This is a reason to know the original data sources as well. To be sure, there also are commercially available economic databases that professional economists subscribe to, which will be much more comprehensive and include for pay specialized data sources. Nonetheless, for our purpose, FRED or DataZoa, which are the 2 consolidated economic databases that we began this course discussing, are more than sufficient. Although we have not done much with DataZoa, which is used by the University of Arizona's forecasting project, both DataZoa and FRED are resources that you always will have access to well after this class ends. This ends our discussion. Of course, Chapter 7 in the textbook has more detailed calculations for topics that we discussed here. If something is unclear in your readings, please raise a question with me, and I will be happy to clarify or explain something in more detail. However, for this discussion, I tried to focus on the key concepts, rather than the minutiae of the calculations. Finally, take a moment to consider the questions on this slide.